here to discuss sag and crest vertical curves, their components and how to compute those components, and how these curves are of help to road users. Before putting ourselves in the discussion of sag and crest vertical curves, let's discuss about passing sight distance. Appreciable grades increase the sight distance required for safe passing. Passing is easier for the vehicle traveling downgrade because the overtaking vehicle can accelerate more rapidly than on the level and thus can reduce the time of passing. But the overtaken vehicle can also accelerate easily so that a dangerous situation may result. The sight distances required to permit vehicles traveling upgrade to pass safely are greater than those required on level roads because reduced acceleration of passing vehicle, which increases the time of passing, and the likelihood of opposing traffic speeding up, which increases the distance traveled by it. Compensating for this somewhat are the factors that the passing usually loses some speed on upgrades and that many drivers are aware of the greater distances needed for passing upgrade compared with level conditions. If passing is to be performed safely on upgrades, the passing sight distance should be greater than the derived minimum. Now, we immerse ourselves into the concept of crest vertical curves. The crest vertical curve is a vertical curve having a convex shape in profile and is used for positive grades, or climbing grades. The main design consideration at crest vertical curves is that of sight distance. At all crest vertical curves, the stopping sight distance corresponding to the design speed must be provided as a minimum, although wherever practicable provision of greater sight distance is desirable. In particular on single-lane and two-lane two-way roads, provision of intermediate sight distance or greater is desirable where it can be economically justified. On these roads, overtaking sight distance usually can be provided only in flat country where grade changes are small. The main factors to be considered when determining the length of a crest vertical curve are the change of grade to be accommodated and the length of sight distance to be provided. In any given case, the change of grade is largely dictated by topography and general longitudinal grading considerations, including practical and economical factors. However, in many cases there may be scope to alter one or both grades to obtain an optimum solution, hence fixing the final grade line is often an interactive process to obtain the most satisfactory combination of grades and vertical curves. In computing for components of the following formula is followed with the corresponding components of it written below. Basically this is the general equation used for vertical curve analysis. Sag vertical curves are curves that connect descending grades, forming a bowl or a sag. Designing them is very similar to the design of crest vertical curves. They are seen in negative or descending grades. Sag vertical curves connect descending grades, forming a bowl or a sag. Once again, such as in the case of crest vertical curves, the sight distance is the parameter that is normally employed to find the length of the curve. When designing a sag vertical curve, however, the engineer must pay special attention to the comfort of the drivers. Sag vertical curves are characterized by a positive change in grade, which means that vehicles traveling over sag vertical curves are accelerated upward. Because of the inertia of the driver's body, this upward acceleration feels like a downward thrust. When this perceived thrust and gravity combine, drivers can experience discomfort. The length of sag vertical curves, which is the only parameter that we need for design, is determined by considering drainage, driver comfort, aesthetics, and sight distance. Once again, the aesthetics and driver comfort concerns are normally automatically resolved when the curve is designed with adequate sight distance in mind. Driver comfort, for example, requires a curve length that is approximately 50% of the curve length required for the sight distance. Drainage may be a problem if the curve is quite long and flat, or if the sag is within a cut. The theory behind the sight distance calculations for sag vertical curves is only slightly different from that for crest vertical curves. Sag vertical curves normally present drivers with a commanding view of the roadway during the daylight hours, but unfortunately, they truncate the forward spread of the driver's headlights at night. Because the sight distance is restricted after dark, the headlight beams are the focus of the sight distance calculations. For sight distance calculations, a 1-degree upward divergence of the beam is normally assumed. In addition, the headlights of the vehicle are assumed to reside 2 feet or 0.66 meters above the roadway surface. As with crest vertical curves, these assumptions lead to two possible configurations, one in which the sight distance is greater than the curve length, and one in which the opposite is true. The figure below illustrates these possibilities. As with crest vertical curves, each possibility has a different design equation. All that you need to do, therefore, is make sure that the results from the equation that you use are consistent with that equation's assumptions. For example, if you employ the equation that assumes the sight distance is greater than the curve length, you should make sure that the resulting curve length is less than the sight distance. Here are the formulae for sag vertical curves for both cases of S and L comparisons. Depending on the components given or required, any of these equations may be used. The stopping sight distance is normally the controlling sight distance for sag vertical curves. At decision points, the roadway should be illuminated by other means so that the sight distance of the driver is extended. Where possible, increased curve length may also be provided. Highway overpasses or other obstacles can occasionally reduce the sight distance on sag vertical curves. In these instances, separate equations should be used to determine the correct curve length. These equations are readily available in design manuals. At this point, you have all of the information that you need to develop the precise layout of your vertical curve. The parabolic curve calculations are identical for sag and crest vertical curves. Just remember to use the appropriate positive or negative values for the participating